want to say hi to everybody. It's always a tough act to follow the great Jim Head. One of my co-authors is also Renee Weber on this. We'll go to the first slide. Next slide, I'm sorry. Okay, for those of you who are completely unfamiliar with lobate scarps, let me just give you the brief history. They were first found in primarily high-resolution panoramic camera images. These are small thrust fault scarps that were again found primarily in the highlands to start, but the coverage, the high resolution coverage was so limited that at the time, that era, we only knew of about tens of these scarps' existence. With LRO, LROC images, we have now found literally thousands of these young thrust faults all over the moon. Next slide. And that includes the South Polar region. You can see a bunch of them scattered around here, these little red blobs, because they are so small, they don't really resolve very well to scale. There's an example up in the right, the upper left corner of a small cluster, the Whitechurch cluster, which is located to the sort of the southeast of the pole. Next slide, please. So there are, in fact, 15 of these lobate scarps mapped within 150 kilometers of the South Pole, some as close as 60 kilometers. The closest are in, and forgive me, hopefully the family will forgive me for the De Gerlach Rim 2 area. There is a small cluster of these, again, within 60 kilometers of the pole and in the actual study area. So about half of that 15 those scarps are within 120 kilometers of the pole. Next slide. So the largest of the De Gerlach scarps is about 4 kilometers long and occurs on a poleward regional slope. And using LOLA shot data, topographic profiles show that the virgin side of this, in other words, the scarp face, is on the downslope side, which typically I get suspicious of when I'm trying to make a definitive determination of a thrust fault. Prefer to see them on the upslope side. But when you look at the topography, mainly the shape of these features and the scale, the relief on them, which goes to 60 to 80 meters, they're fairly consistent. And one of the things that Gareth pointed out in his talk is how blocky the scarp face is, which adds additional support to this being a thrust fault scarp. Next slide. Okay, so if these young faults are indeed active, they are going to generate moonquakes. And the Apollo Seismic Network, many of you know, detected 28 of these shallow moonquakes. Some of them were very strong, up to Richter equivalent scales of 5. And the source of many of these shallow moonquakes was largely unknown. So we did a study in 2019 that we published where we looked at, basically, we relocated the epicenters of the blue dots on this map are the original locations, and the small black dots are the clusters of possible locations of the epicenter relocated using an algorithm that's designed to deal with sparse seismic networks. Next slide, please. Okay, so it turns out that of that 28 shallow moonquakes, one of the most strongest occurred in the South Pole area, and that's located in this image on the left by the little green dot was that location, but it occurred in March of 73. It's the N9 event, and it had a body wave magnitude estimated to be 5.6. And if you look at the distribution of the relocated epicenters, which are these magenta dots, you can see that actually one of those dots is within 24 kilometers of the de Gerlach scarp. Next slide, please. So what is the expected seismic moment and stress drop that would be expected if a slip event on that fault caused this shallow moonquake? Well, we can figure that, or we can at least estimate the seismic moment using this relationship, which I have, and I don't have time to talk about it. It's described in the abstract, so if you're interested, I refer you to that. The main point is that the estimate, essentially, the moment magnitude based on that estimate is about 4.9, which agrees pretty well with the calculated magnitude of the N9 event. Now, the stress drop that accompanies a quake is a good indication of the magnitude of the regional stress field, and we can estimate that stress drop associated with a 4.9 event using this relationship for a rectangular fault geometry. And we get approximately a 1.3 MPa stress drop. And a 1.3 on, formed from, again, this is a slip event that, again, just to be clear, we're talking about the entire scarp being formed in one event, so this is kind of, again, an extreme case. It's probably unlikely that any of these low-baked scarps got all their structural relief in one event. But at any rate, a stress drop of 1.3 is within the range that we think the model stresses, global compressional stresses, which is encouraging. And I just included this diagram of the seismogram to entice everybody on the need for a new global seismic network on the moon. Next slide. Okay, so what is the origin of the stress that's causing these young thrust faults? Well, primarily, it's coming from global contraction, we think, from ongoing interior cooling, coupled with tidal stresses from orbital recession and a small contribution from diurnal tides. The tidal stresses are superimposed on global contraction stresses, and they result in a maximum of somewhat over 2 MPa, and you can see the distribution in this map. And that blue dot at the very bottom is the N9 event. Now, from the stress models, the maximum stresses are predicted near the tidal axes when the moon is at apogee. But it turns out, if you look at the distribution of where the shallow moonquakes occurred during their, in the orbital phase, you can see that the N9 event there by that black arrow in the upper diagram occurred at perigee, not apogee. And it's certainly not located near the pole, where, again, the stresses should be the greatest. And this probably indicates that the stresses at the pole are mostly the global contraction component, with only a small contribution coming from any tidal stresses. Next slide, please. Okay, so what would a 4.9 event look like? And so we've done that model for the de Gerlach location at a depth of about 350 meters. And you can see from the diagram on the left, upper left, that, and we've got the Mercalli intensity scale there, so you get a sense of just what we're talking about in terms of strength of seismic shaking, that you can see that we're predicting pretty strong, moderate, at least to strong seismic shaking as far out as maybe 30 kilometers from the source. And, probably light shaking far greater than 40 kilometers. The map at the bottom is showing the extent of severe or great shaking, which is defined as 2.3 times the acceleration due to gravity at the moon. Next slide. Okay, and you can see if you can activate that. Are you getting a play? Okay, this is again that 4.9 event simulation, the vertical displacement. First of all, this is not meant to scare anybody or scare anyone off of this site. It's just to give you an idea. This simulation includes both body waves and surface waves, as well as scattered waves. But it's pretty impressive, showing just how far off or how far out from the source this you can expect significant displacement. Next slide. Yeah, you may have to click it a couple times to get past it. Okay, so what is the expected result of a seismic shaking event of any magnitude at the South Pole? Well, the most likely result is going to be landslides. So what I'm showing you here is essentially a landslide susceptibility model that suggests that a large portion of the interior walls of Shackleton Crater could experience landslides. The model is based on the ratio of the shear strength and shear stress, the angle of internal friction, and the cohesion of the regolith. And you can see from the dots here, that little legend at the bottom, one of the critical parameters is the assumed incident, the angle of internal incident, or the angle of internal friction, sorry. As you increase that assumed angle from 30 to 35, the area of susceptible landslides is greatly reduced.
Hey, Tom, we are at limit, so if you have a conclusion.
Yes, you can go to the last slide, and I think it would be the... Okay, this is just to show that we now have some images thanks to ShadowCam of the Shackleton. And in fact, we do see some evidence. We see clear evidence of a boulder fall and some evidence of some landslide activity. Okay, we can next slide. Sorry, I'm running over here. This is one of my favorites, just to show what a good terrestrial analog to a lunar lobate scarp might be. This is the Meckering scarps that were formed in a 6.3 quake in 1968 that had as much as 1.5 meters of displacement. But the key thing is that they're shallow faults as well, and their stress drops are right within the range. And this is probably because we're looking at interplate quakes. Last slide. I'm done, and I'll end there.
Great, Tom. Thank you.